Hi, AP Physics. Today we are going to be learning about the center of mass and how it relates to momentum and also to the conservation of momentum. So the first thing is, if we have two objects, let's say one small and one big, where in the distance between their centers is the center of mass? Now, the first thing is, the center of mass is simply the average position of their mass. Now, we have the distance between them, and we would imagine that, right, there's a lot more mass on the big object than the small object. And so we would imagine that the center of mass might be somewhere over here, right? But exactly where is it? How could we calculate that position? To do so, we are going to be using the equation x for the center of mass, right? That's x for position, center of mass, is equal to the mass of our first object. Let's make this our first object. We'll make this our second object, multiplied by its position, plus the second object multiplied by its position, divided by the addition of the two masses together. Now, we can easily make x1 equal to 0, and so this equation might simplify into mass 2 over x2 divided by the addition of the two masses. Now, it might be the case that our system is a little more complicated. We have more objects that we're going to have to account for. So let's make this equation a little more inclusive to multiple objects, not just two. So we're going to have our position of our center of mass, and that is going to be equal to 1 over the total mass of our system. So 1 over capital M. And then we're going to use a sigma to represent that we're adding all of our positions and the different masses at those positions. Now, this is also helpful in case our object, let's say we're actually trying to solve for the center of mass of one object, but the density of our object changes. So it's going to be a delta M instead. So how does this relate to momentum? Well, let's put our let's consider a box, right? And this box has some explosives inside it. And so at some time later, one half of the box is going to be over here, and the other half of the box is going to be over here. All right. Now let's say they both have the same mass. We'll call it mass M. And they've been moving for just a little bit of time. Now, at the very beginning, right, my momentum is going to be equal to 0 Newton seconds. Okay? And afterwards, since momentum is conserved and all of the forces are internal, we're still going to have 0 Newton seconds of total momentum, right? But each of the boxes are going to be moving. Another way to think about this is concerning the center of mass. We can consider our system to be moving together. So if we had some initial motion, then we would see the center of mass moving with that motion, even if our object breaks up into several pieces. And so we can actually look at that here. Since both sides of my box has equal mass, right? They both should have the same amount of velocity, but going in opposite directions. Now, we can also consider the center of mass here, right? The center of mass in the very beginning was right in the center. Actually, let me change my color here. Right? The center of mass was at the very center. And since both of my boxes have been moving at the same time with the same velocity, right? The center of mass is in the same spot. So this is one way to think about it, is that instead of trying to find the individual momentums, we can actually find the center of mass. If the center of mass didn't go anywhere, then the system still has the same momentum. This is what the book talks about when it's considering thinking about the momentum as a system of particles. We can look at the center of mass of those particles. So here we see the center of mass is in the very center of our box, right? Stationary, but at some time later, the box has exploded. The two pieces are moving away from each other, but the center of mass is still right where it was before. And so this can help us understand that the total momentum of our system is still zero because there's no velocity to our center of mass. It hasn't moved anywhere. Now, what about objects that don't have a consistent density, or they're not circular or in a line, so you can't just assume where the center of mass is going to be? In this case, we are going to have to do an integral. We're going to have to integrate all of the little bits of mass that make up our object. So that integral is going to look very similar to our previous equation for the summation of all the masses and their positions. So if we're going to find that center of mass, right, that position of the center of mass, we are going to first pull out the total mass and then integrate our different positions and the small bits of mass that make them up. Okay? But if we integrate, right, we're just going to get R and M, mass times radius. Well, this isn't always true, right? The density is going to have to be taken into account. So density is the amount of mass over the area that it's in, or that's in 2 dimensions. If we want 3 dimensions, that we're going to have to divide by volume, right? The units is going to be kilograms per meters cubed. So that's what we can do here. We can split this up and plug in our density. So let's consider a rod of even density that has a length of L, right? So this is one-dimensional. So they take the total mass and they divide by the length. That's going to be our density. And so this relates mass with position. So now we can actually solve. So let's rewrite our equation so that it solves 1 over the mass of our rod. And we're going to be integrating over the position 0 to length L on the other side. Since we're in one dimension, we don't have to consider any other x, or we don't have to consider a y and z coordinate. We just have an x coordinate, dm. And we know that each little bit of mass is equal to and let's look at a little slice here. We know that this little bit of mass is going to be equal to the density multiplied by our little change in x. So we can plug that into our equation. That's going to give us 1 over capital M, integrating from 0 to L, x. And instead of dm, we're going to write the density and with respect to our little small portion of x. So notice how in our problem here, we are changing our dm into some relation with respect to dx. And that's what you'll be doing when you do your center of mass calculus, is you're going to have to change that into units of position, or a small change in position, a dx. In the problem on the homework, if you have an area, let's say we have a box, we will have to integrate the area. So we'll have some dA, and we'll need to relate that to the mass as well.